Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll look at higher degree expansions. We've already looked at things like x plus 3 squared. Now we're looking at x plus 3 to the power of 4. So we're looking at expansions where the power is higher than 2 because it gets a bit more complicated. Now, if I wanted to use FOIL on this, I'd be multiplying x plus 3 by itself 4 times. Now, this gets complicated very quickly. It might look simple, but really you've got to make sure you multiply everything in the first bracket by everything in every other bracket. Then you'd have to do the same for the second bracket. You'd have to take everything in the second bracket, make sure it's been multiplied by everything in each other bracket, and so on. It would just take forever. So we need a quicker way to do this. Now note, any term in this expansion, it will involve multiplying 4 of these things together, a combination of x's and 3's. So our terms for this, there's going to be a term that's just x to the power of 4. There's going to be a term that's x to the power of 3 times 3. There'll be one that's x squared times 3 squared. Now notice here that each time the powers are adding up to 4, and that's of course no coincidence. They add to 4 because the power of the original expansion was 4. So the way that you can approach this is just start with the first term, in this case x, start with the power of the expansion, and each time decrease the power of that by 1. So x to the power of 4, 3, 2, 1, and x to the power of 0, I don't even need to write. And then for the second term in the brackets, you do the opposite. You start at the first term, but each time you increase the power. So starting at 0, so 3 to the power of 0, I don't even need to write. 3 to the power of 1, 2, 3, 4. So these give you the terms. But we're not quite done here. See, between each of these terms, there is going to be a coefficient. Now, how do we know what the coefficients are? Now, fortunately, Pascal's triangle helps us with that. So to construct Pascal's triangle, we start with a row that has a 1, the next row has 2 1s, and for each subsequent row, we start and end with a 1, and in the middle we add. We add 1 plus 1, it gives us the number in between them. Next row, 1, 1 plus 2, 2 plus 1. Each row starts and ends with a 1. So the next row will start and end with a 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and so on. You could keep going and going. So in Pascal's triangle, this first one is in row 0. So this is row 1, row 2, row 3, row 4. So each starts with entry 0. So for example, this one here is entry 0 in row 4. So this is row 4 entry 1, row 4 entry 2, and so on. So how do these numbers help? Well, when we're expanding to the power of 4, the coefficients for each of these terms are precisely these numbers from row 4 of Pascal's triangle. So in front of them, I put 1, 4, 6, 4, 1. So now I'm just going to simplify. X to the power of 4 times 1 is just x to the power of 4. So the next term is 4 times 3, so 12x cubed. Next up, we have 6 times 3 squared, 6 times 9, 54. Then we have 4 times 3 cubed, 4 times 27 is 108, and the last one is 3 to the power of 4, which is 81. All right, let's now look at another example of a higher power expansion. So let's expand this using the techniques from the previous slide. So what we do is we start with the first term to the power of the expansion, and with each subsequent term, as we go from left to right, we decrease by 1 the power of this first term. So we keep going here until we get to the power of 0. So now we take the second term in the brackets, which is not 3, it's actually negative 3. So we start at the power of 0, and this time we're going to increase the power with each subsequent term from left to right. So note that for each of these terms, the powers add to 5, which is no coincidence. They should add to the power here. So we're going to put a plus between each of these terms. Now, each of the 6 terms needs a coefficient. How do we get the coefficients? From Pascal's triangles. So row 0, row 1, row 2, we're going to go all the way up here to row 5. So that's row 3. Row 4 has 4 as its first entry. Remember that we always say this one is entry 0. So row 5 will be 1 at both ends. 1 plus 4, 4 plus 6, 6 plus 4, and then 4 plus 1. This is the row we want. This is row 5. So the coefficients will be 1, 5, 10, 10, 5, 1. Now we just need to simplify each term. So note that anything except 0 to the power of 0 gives you 1. This is just 2x all raised to the power of 5. So 2 to the power of 5 is 32. So we've got 32x to the power of 5. So over here we have 5 times 2 to the power of 4 is 16. So that's 80 times negative 3. So negative 240 x to the power of 4. Now we have 10 times 8 times negative 3 squared, which is positive 9. So we get 720 x to the power of 3. So the next term following on that will be negative 1080. Hopefully you can see a pattern here. When the second term in the brackets is negative, as it was here, every second term is negative. This term here is going to be positive. It's going to be positive 10 times positive 81, so 810x. And the last one will just be 3 to the power of 5, but negative. Every second term is negative. All right, we are done. Thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.